Hi, welcome to today's session on graphical transformations. So what we're going to be doing, we're going to be looking at a function which has created a line using an equation, and we are going to be conducting transformations on this. The transformations we're going to be looking at are translation, stretching, or we also call that enlargement, and reflection. So we're going to start off with a graph which has got an equation that we're going to just call y equaling the function of x, the f of x. Now what we can do is produce, if we add a to this function, so adding a number or some form of unknown to this function, we are actually creating a translation where, as you can see, this entire line has been moved upwards. It's been moved up by the vector of 0 over a as our column vector. If we had minus a on our function, then we'd actually be translating this in a downwards direction. That's because if we've got a positive number at the bottom of our vector, we are moving upwards. If we've got a negative number on our vector on the bottom, we are heading downwards. So we are literally taking our line and shifting it up or shifting it downwards, dependent on if this is plus or minus a after our function. Here we've got x minus a actually within our function. And what you can see here is that it has translated to the right. It's been shifted to the right this time, which means that it's actually translated by the vector of a over 0. If we had x plus a within our bracket, so our function adding a, what we're actually doing is we're translating leftwards. We're translating to the left because we have a negative number. So it's worth noting, if we've got a positive number at the top of our column vector, we are moving to the right. If we've got a negative number on top of our vector, we are moving to the left. Another one is where we've got a multiple of our f of x. This actually creates a stretch. This actually creates an enlargement, but what you can see here is that it's actually been stretched vertically to the scale factor of a. So whatever this number is or unknown is, that is our scale factor. So as you can see, all the x points have not moved. The x coordinates of the x parts of our coordinates, the x values of our coordinates have not changed, and they have a special name, invariant points, because they don't change. As opposed to if we've got our scale factor actually next to the x, so we're looking for the function of ax this time, we are creating a stretch or enlargement, but this time we are stretching horizontally. And this is to a scale factor of 1 over a in the x direction. So just the same as what we saw just when we've got a in front of our function of x, this time our y points do not change, our y values within our coordinates, and these are called as well invariant points. Our next one is if we've got a negative function of x as opposed to our function of x, and as you can see, this creates a reflection in the x-axis. As opposed to if we've got a negative x, a function of our negative x, this actually produces a reflection in the y-axis of our line. And that was all of them. If you like what you see, please subscribe. Thank you very much for watching.